Hello, everyone, and welcome to our educational course on open and reproducible neuroimaging from study inception to publication. I'm Botvinik-Nezer. I'm a postdoc at Wegerslet, Dartmouth College, and incoming faculty at the Hebrew University of Jerusalem. And today in this course, you're going to hear from wonderful speakers, including Yumar Niso, Aaron Rear, Jochen Rieger, Aga Karakuzo, Yarek Elchenko, Piero Lotz, and Franco Bastilli. But let's start with some background and context for why we're teaching this course. So many studies, particularly in the last decade, have shown that performing open, reproducible science is beneficial for scientific progress for each one of us individually and together as a community. It increases the credibility of published findings, allows other researchers to reproduce, replicate, generalize, build upon previous research, thus extending the scientific knowledge. But yet the adoption of open reproducible practices is still limited compared to the benefits in general and specifically in neuroimaging. So just to give some examples, a recent survey by Pareto et al. Have found that 42% of responders have never pre-registered a neuroimaging study, and about 1/3 have never shared their raw data. And since many of those who indicated that they pre-registered or shared their data at least once, likely did not do so, in all their studies. And also researchers who are using these practices are more likely to respond to such surveys. It's reasonable to assume that the actual rate of these practices, registration, sharing data, and other open reproducible science is actually much lower than this indicates. And again, this is a thought with the known benefits of open reproducible practices, and also with recent top-down changes where different journals, funding agencies, institutions are increasingly requiring the researchers to share their data and reproduce the results or pre-register their studies. And we think that one of the main challenges to the adoption of open reproducible practices and tools is that there are abundance. Just so many tools, so many practices that exist. And it's really hard, even for experienced researchers, or even for ones that are involved in the open science community, to know all these tools and understand how they fit together, which ones we should use, and how, in our own research. So this is why we're here for. And the aim of this educational course is just to present an integrated overview of all these tools and practices, combining the theoretical background and some practical demonstrations to show you how in every step of the research cycle, from the study inception, through the planning, acquisition, research data management, data processing, analysis, and then finally dissemination, publishing, which tools exist and how you can use them to help your research make it better, more reproducible, more open. And this educational course follows the line of a recent review that we published as a group of 20 researchers from different labs around the world that are actively developing or using open science tools in neuroimaging. You can use the QR code here if you want to access the paper. Just look for it. It was published in 2022 in Neuroimage. And in addition to that paper that we published, we also developed an interactive live online resource where the content of the paper, the review, exists, but it's more dynamic, and we can update things there as we go. And we will also put educational course materials there for public use. Again, there's a QR code that you can use to access it, or you can use the link above here. And I really recommend using it, and as an additional source with a lot of information about the different tools, and also links and references to other resources. And particularly what we did was we prepared a huge table with many external resources for each research stage and topic. This is available as supplementary materials for a paper and also on the online resource here. So I really invite you to use it if you want to focus on a specific topic. You could see a few resources that will be very useful for you, when you want to use these tools or start using these practices. And following this introduction, I will briefly cover the research planning stage, and then we'll focus on pre-registration with some hands-on opportunity and time for questions. Then you will hear about consent and data sharing, data acquisition, quality control, data management, how to organize, which standards exist, how to track the data. Then about data processing and analysis, and finally about research dissemination and publishing. And then we will quickly summarize the course and have time for final Q&A across the entire sections. We will also have a break in the middle, of course, because it's pretty long. So now I will dive into the first stage of the research cycle, the inception and planning. Again, briefly discussing the preparation and then focusing on pre-registration. after me, you will hear about ethics and data sharing, data acquisition, and then we'll go back to quality control. So let's imagine a scenario. You invested hours, you got help from research assistants, from colleagues. You worked really hard, a lot of time to recruit participants, to make sure they complete those sessions, to run the experiment, to collect your data, to make sure everything is working. And finally, after a month, years, your expensive data set of, let's say, 80 participants is ready to be analyzed. You sit on your computer and you start to work on the data, but then you realize that you did not log the timings of the different stimuli. So now you cannot connect the brain responses with the specific events or things that happened during each point in time. So what do? Well, the best thing is actually to avoid getting into this situation in the first place. So to do so, we need to carefully plan and prepare for the experiment and not run forward and just start doing things without being ready. And at these days, data sets are getting larger, data become more complex, so planning becomes even more essential because we want to increase the likelihood that the project will be successful, it will have minimal data loss, the data will have high quality, and that we can analyze it to test hypotheses to want it. And such preparations include, for example, collecting a few pilot participants before starting the actual data collection. So what we usually do, we just take a few participants that are not going to be included in the final data set, and we use them to make sure the experiment is ready, participants understand instructions, everything is working properly, the experimenters know what to do, timings are as planned, we can perform a preliminary analysis on it. We have the variables that we need, we have the data that we need, we have the logs that we need. Nothing is missing, everything is complete, data are backed up or saved where they should be, devices are working, And in many cases, you could also use existing data sets in your lab or open ones or simulations to pilot some things like the analysis. But of course, this does not test whether participants understand instructions or whether experimenters know what to do with the device is working. So it's really recommended to actually run a few pilot participants. Another important aspect of planning is to prepare a standard operating procedures document, SOP. This document ideally describes everything about experimental procedures, how you recruit participants, how you prepare before they come, what they do once they do, which devices needs to be connected, how, when, why, which script to run. You should include also the instructions given to the participants as a script, what experimenter should tell the participant to make sure different experimenters are saying the same thing, or the same experimenter is saying the same thing to different participants, because this will affect results. What to do with the data at the end, how to pay them, everything should be there. And this document ideally should be dynamic, so if you spot mistakes, if something changed, something doesn't work, experimenters don't understand something, participants don't understand something, you should update it in the SOP. And this SOP is very useful both for making sure the experiment runs smoothly and the same across participants and experimenters, or to onboard new experimenters, but also when you write a method section of your paper, it has a lot of details that are usually very important. Which version of MATLAB you use, if you're using MATLAB, or which version of other software you use, things like that. And ideally, if you give this SOP to someone else external, they could run your experiments from start to end without needing your help, just for understanding everything from the document. And also, ideally, this should be shared along with the data set or the publication, so that other people can reproduce and replicate your results and know exactly what you did, because this could provide much more information than the method section could. It's really good to get some examples of SOPs from your colleagues in the lab or in labs doing similar things. But if it's not possible, there are also public examples of SOPs and protocols, for example, protocol exchange, protocol IO, and nature protocols. But even if the study is well planned, piloted, there's SOP, everything is should be. There are many biases and challenges that still affect their reproducibility and credibility of studies. Just to give some examples, scientists are humans, we're all human, and human reasoning is known to be biased by our prior beliefs, by our preferences. And this is problematic, particularly in the current atmosphere of science, where the emphasis is more on significant, surprising, impactful results compared to more careful, rigor, replicated, accurate ones. It is changing, but it's changing slowly. So this could be a big problem. And also, there's high flexibility in data analysis. It's growing as methods become more sophisticated, and this also contributes to decreased reproducibility and credibility. You will hear about more later today. There are some specific questionable research practices that should be minimized, such as erking, hypothesizing after the results are known, which refers to changing the hypothesis after one already knows the result, and p-hacking, which refers to the too common practice of consciously or unconsciously exploiting the flexibility in that data analysis and testing many different analysis pipelines, but then reporting only the one that yields the significant or desired or the expected result, which is actually a huge problem. So one of the solutions to this problematic practices is pre-registration. Here there's cited from Nosek and Lindsay. Pre-registration is the specification of a research design, hypothesis, and analysis plan prior to observing the outcomes of a study. And the idea is that you publicly state your hypothesis in a plan before you collect the data, or at least before you perform the analysis. And therefore, erking or p-hacking are less possible because it's clear what you hypothesize before and what not, and what you plan to do before and what not. In other words, what pre-registration does is to distinguish between exploratory research and confirmatory research. And exploratory research is when you use your data to generate new hypotheses, and confirmatory research is when you use the data to test pre-existing hypotheses. It is really important for me to note at this point that both exploratory research and confirmatory research are really useful, very important to research. We need both. We need to generate hypotheses and we need to test them. But each one of them requires different tests, and the conclusions that can be inferred based on them are different. So therefore, it's important to distinguish between them. So pre-registration is submitted to a public registry. It gets a timestamp of the frozen process version that cannot be changed. And then, you can make updates, but the updates will be saved in a different, there's a different version. So you can see the raw version and the timestamp, and the update and the timestamp. You can just explain why you did and the update that you did. There are different registries for pre-registrations. The three main ones are the Open Science Framework, OSF, which also has a lot of different types of registration and allows you to do other things like share your data, share your code, share a lot of documents, and give some more information. As predicted, is a more simplified platform, which we will look at later. And the NIH and clinicaltrials.gov website is what people use to really to pre-register clinical trials. That you have to pre-register there. So why is it good to pre-register? Pre-registration improves transparency, and as I already said, it prevents, at least minimizes questionable research practices such as p-hacking and erking. It also improves planning, helps spot mistakes in time, since the plan is agreed upon prior to data collection, or at least prior to the analysis between the different co-authors. And finally, for individual researchers, there are different forms of recognition. For example, there are some open science and specifically pre-registration badge that the publication could get in some journals. There are certain awards that are given based on such practices. In general, it's seen as more rigorous research. A more advanced form of pre-registration is registered reports, in which the pre-registration is actually submitted to a journal. So it's more detailed. In the first stage, what you do is you submit the introduction and method of a paper. So what is the background, what you're going to ask, and how you're going to do it. There are hundreds of journals that accept these types of papers, the pre-registered reports. You can see a list in this thing that you see on the slide, where I took this figure from. So you can choose a journal, submit your plan to it. Then it goes for peer review. Usual peer review can be rejected, revision, minor, major. If it is accepted at this stage, it means it got an in-principle acceptance. And this means that if you now go and perform the research that you said you're going to perform, and then report back, then this will be accepted to the journal. So if you got this in-principle acceptance, you collect your data, perform your analysis, you write a paper, as you usually do. And then this final paper goes through stage 2 peer review in the same journal. And this peer review is focused on whether you did what you said you're going to do and whether your conclusions are supported by your data. So it's not about now if the results are significant or cool or whatever, because already in stage 1 it was prove that what you want to test is important, it's interesting, and you do it correctly. Your plan is good to test this hypothesis. So if you did it and your conclusions are reasonable based on the results you got, this should be accepted and then published in this journal. So now for the remaining time, I want to take about 7 minutes for an hands-on experience with pre-registration. What I would like you to do is to think about an experiment that you're planning or an experiment that you're performing now, or recently finished. And in your browser, go to aspredicted.org or use this QR code. Create a new pre-registration. Make sure to check this purple text box that says, just trying it out, make this pre-registration self-destroy in 24 hours. You can see here in the screenshot. And as predicted, is a simplified version of the pre-registration, less questions, less requirements compared to most of the versions of OSS and clinical trials. So let's just try to go over the questions, each one of us. And for the experiment that you have in mind, answer them in writing or in your mind for this experiment. Think about, challenges that you encounter, questions that come up, what's easy, what's hard to fail, and why. And then afterwards, we'll have time to ask questions, and we can talk about it more. For this pre-recording, because we won't be able to do the Q&A, what I'm going to do is to go over some common scenarios and questions that usually come up and give some answers about them. So first, what do you do if you're planning an experiment for which data have already been collected? The answer is that you can pre-register anything that have not been tested yet, but it should always just be transparent. What data exists, what you already tested, what you already analyzed, what you already know. This is because we want to make sure everything is clear and transparent, and that researchers who call for your pre-registration could estimate whether and how biased you were when you pre-registered your analysis. Second, what do you do if you don't have specific hypotheses and predictions? Well, so like I said before, exploratory research is very valuable and as essential as confirmatory research, because you do need to generate hypotheses to be able to test them, but it is less relevant for pre-registration. So when you publish your exploratory findings, just report them as such. Don't pretend as if you had predictions. Don't use language like as predicted or as expected, because you did not predict it before. And also, main recommendation is if you do exploratory research and come up with new hypotheses, to test them in your data, replicate them. And if this is what you're doing, you can do exploratory research and then pre-register the hypotheses that were generated from your exploratory analysis, and then test them in a pre-registered study. What if you pre-register your plan, but then something changed? Well, this is super common. If you hadn't run the analysis yet, you can just update your pre-registration as we discussed before and explain the change, and people will be able to see the update. If you already did it, just report and justifying the paper, the deviations from pre-registration. Usually we use a section named deviations from pre-registration or something like that in the method section, and just explain what changed and why. And it's also recommended, and you should report the results of the original planned analysis. This might be, you might be able to put it in supplementary materials depending on the circumstances. What if you want to pre-register but you're stressed with time? So first of all, in the long term, pre-registration should actually save time, because data analysis is well planned and coordinated among the researchers team from an early stage, preventing mistakes and complications. But if you can do it now, you have to start collecting data or have to analyze the data. Just do what you can. Even just pre-registering your planned sample size and your hypothesis is a big step forward. And next time you can do more. I will also say that applications studies are much easier to pre-register. So if possible, you can start with such an experiment. It's really easier because you know what you're going to do and what the hypotheses are. What if you're worried about scooping? So scooping is when someone steals your ideas and publishes them before you. So first of all, I want to say that I'm not aware of any case of scooping because of pre-registration, but also that pre-registration actually can protect you from that, because there is a public record with timestamp your plan and your hypothesis. But also pre-registration, all the different platforms allow you to keep it private for a while, either forever or for a few years. So what usually people do is to pre-register their studies, keep it private, and then only when they publish the preprint or the paper, they make it public. And then no one can scoop on anything, because no one can see your pre-registration before you publish your paper or before you decided this is time for you to do it. What if you made a mistake in your periodization? So first of all, everyone makes mistakes. So good job copying it and spotting it and correct it. If we didn't analyze the data yet, we can just update your periodization and explain. If you analyzed already, just go back to the slide about the deviation periodization. Just explain what will change and why, and report the periodic analysis, universal complementary data, or depending exactly on the changes somewhere in the paper. Again, the key is just to be transparent. That's the idea. So just to sum up, here are some resources about periodization, including templates for different types of studies, examples, recommendations, educational materials. And as I said before, you can also find a lot of information on our paper and our online resource. Thank you very much, and good luck with periodization.
Hello, my name is Jochen Rieger, and I will give you a short introduction into ethics and data sharing plan. So first, a problem statement. So I think many of you experienced already that the regulations for protection of personal information is a big source of uncertainty. Different regulations exist across fields, actors, and different jurisdictions, and several surveys show that this can demotivate data sharing quite a bit. And if you were one of those who basically gave up in this jungle, I hope that I can give you here an overview that motivates you, because the good news is it is manageable. And it's often manageable with none or even only slight adaptations of your existing procedures. Just a short disclaimer here. This is not any legal advice that I'm giving here. Don't blame me. Now, the first thing that you need to know or that you need to be aware of is what type of data you're dealing with, because the different regulations all distinguish three basic types of data. On the one hand, there are the so-called anonymous data. They do not contain any link to an identifiable person, and they typically can be shared without any restrictions. Only in China, some state protection may apply. The next class is so-called pseudonymized data. They contain both personal information and separated from them non-personal anonymous information. However, these two types of information are linked via a coding list, and the coding list is here the problem. So one thing that you need to make sure when you want to share the data is that the data recipient has no access to the coding list whatsoever. So the simplest thing is destroy the coding list if you don't need it anymore, and the data will become anonymous because you only share the anonymous part. The other approach is to make the coding list inaccessible to any data recipient. And this way, you can also consider the data as functionally anonymous. And then, and this is the most problematic class of data, is the special data. They always link to an identifiable person, and they require special protection. Special data are, for example, biometric data, for example, genetic data, that can't be anonymized or pseudonymized. However, the status of neuroimaging data, whether they are special data or not, is currently under discussion. And the current demonstrations of re-identification from neuroimaging, functional neuroimaging data, or EEG, MEG, or whatever, are not really conclusive. So that one can consider them also as pseudonymized data, but that's a matter of taste currently. So what do you need to do with your data now that you know in what class they fall? What you typically need is to get specific written informed consent for sharing. And this is something that you're already doing in most neuroimaging studies. You get informed consent for participation in the experiment from your participants. Now, just add an additional consent for sharing to your consent form. If you plan to share data across jurisdictions, get additional informed consent for sharing across jurisdictions. That's the specific part here. Then you should determine the platform where you want to share. And then you should also determine whether you may need a data usage agreement and prepare a data usage agreement. And once you have everything together, your paragraph for the informed consent for sharing across jurisdictions, your data usage agreement, your plan for the platform where to share, you should get an IRB approval for your sharing plan. In the EU, you might also need a legal assessment of your data sharing plan. In some universities, this is already included in the IRB approval process. In China, you might need an additional assessment of your sharing plan by authorities that are specified by the Ministry of Science and Technology. Now, once you have the IRB and you acquired your data, the next steps are to prepare data sharing is to remove personal information. And one simple method is the so-called HIPAA safe harbor method that specifies a list of approximately 18 personal identifiers that you have to make sure that they are removed from the data that you want to share. If you plan to share biometric data on unprotected platforms, then you should consider sharing only derivatives, not the full raw data. That means for anatomical scans, you should deface them before you share them. Defacing tools are included in many tools, like, for example, FreeServer, AFNI, PyDeface, or Bitsynim as a wrapper around different defacing tools. For eye tracking, for example, you should not share the videos because they contain the iris patterns. However, what you can share is the eye positions and the pupil sizes. So in sum, you should consider anonymization techniques when you try to share biometric data. Share them under protection or do not share them at all. So once you have the data prepared for sharing, you have to think about how to make the data accessible. And for that, you have to select an adequate protection level. So anonymized data can be shared without additional protection. Pseudonymized and special data may require data usage agreements in the EU and potentially also in the US, depending on which regulation you are. In China, the state's data sovereignty must be observed, and that requires special procedures for sharing, as I mentioned already several times. You might also consider protected data platforms with access control for special data and sharing across jurisdictions. I'm not going to talk about the specific data platforms here. They will be covered in a later presentation. Now, if you feel, yeah, that sounds manageable to me, but I want to have more background information. Of course, this was only a short summary. You can look into the paper by Eke et al., who give an overview on international data governance, or in the paper of Rea et al., who review regulations for lawful data sharing in Europe, USA, and China, and provide practical hints for sharing. If you are searching for usable consent forms and data usage agreements in your preferred language, look at openbrainconsent.org. They offer several forms and data usage agreements. Thank you very much for your attention, and I hope that the presentation helped you with your data sharing plans.
Hello, everybody. My name is Aaron Rea, and my session today will be on quality control for neuroimaging data. All right, so let's dive right into it. So why should one actually do quality control? Why is quality control important? To address this issue, I would really like you to imagine the following scenario. Let's say you have spent half a year on planning an experiment which you are very excited about. You tried to follow as many standard operation procedures as possible, and you have even pre-registered your study at a pre-registration server, all in the good faith of open science. After that, you have spent several months on data acquisition and can now proudly say that you have a 60-subject MRI dataset. However, when you try to run the analysis on your data, you suddenly realize there is problems. The analysis fails or produces unrealistic results. So when you seek for the source of these problems, you actually take a closer look at your data and suddenly realize there is severe artifacts in your data, which might really likely be due to some malfunctioning hardware, which you could have swapped easily if you would have known. So now you are left with a data set, large data set that you spend many months on acquiring that you cannot actually use because you didn't check the quality of your data after piloting. So I chose this use case to emphasize how beneficial quality control can be to us as researchers. So what are actually the benefits that one could have from monitoring the quality of their data? First of all, as I have mentioned already with my use case here, you can drastically reduce the time and money spent on data acquisition and analysis if you run quality control on your data before data acquisition. Secondly, you can also easily detect system failures or unexpected events in your data if you run quality control on it. This might also help other groups of researchers if you, for example, find out that there is a malfunctioning sensor in the MEG or something similar. Lastly, quality control obviously is an important step to validate your data. And this is also important in science, that you make sure that the data that you run your analysis on is valid data. So far, we have talked about why quality control is important and how it can actually benefit you as researchers. Now, I would like to dig a little deeper on how to actually implement quality control into your workflows. So what can you actually do to test the quality of your data? First of all, you could do positive control analysis. So what are positive control analysis? Positive control analysis basically means that you test your data for a reliable effect, which should be present in good quality data. This could, for example, be activation in motor cortex during a button press if you had an experiment which deployed a task-based structure with button presses. Secondly, and more importantly, you should define quality control checkpoints. This should be done in advance, so before data collection, ideally. And what this means is basically defining exclusion criteria on the basis of metrics which are calculated on your data. So these are data quality metrics. In the domain of fMRI, this could, for example, be the frame-wise displacement as an indicator of subject's movement, or the signal-to-noise ratio as an overall indicator of signal quality. You should then define thresholds on the basis of these metrics, and later on exclude all of your data that have exceeded those thresholds that you previously have set. Now, here is the bad news about quality control. Quality control is unfortunately quite a cumbersome task, and calculating all of these metrics, image quality metrics on your data can be quite time extensive. Moreover, quality control is lacking standardization, which means that QC workflows are often highly individual and idiosyncratic. However, despite these bad news, I also have some good news for you. Good news is that the community is actively developing tools that should assist and support researchers in quality checking their data. Moreover, automatization and standardization of QC routines is an active line of work. For example, there is MEG-QC, which is an assistive tool for the visualization and quality control of MEG data, or Visual QC, which is a similar tool in the domain of MRI. We also have MRI QC, which is a fully automated pipeline for MRI quality control, or Koala T, which is a tool that assesses the accuracy of your free surfer segmentations. Now, on the next slides, I would like to dig a little deeper into quality control in the domain of MEG, and then I will briefly introduce you to one of the HTML reports which are generated by MEG QC, and I will show you the interactive features of these reports. Let's take a step back and motivate why the quality control is important in the domain of MEG. So the signal that's been picked up by the MEG is magnetic fields which are produced by neural oscillations. So the strength of these magnetic fields, you must imagine, is like by the orders of magnitude smaller than, for example, the magnetic field which is produced by the Earth. So the sensitivity of the sensors which pick up the signal is very, very high. But this unfortunately entails also that these sensors pick up a lot of noise. So there is measures against this, like magnetically shielded rooms, but nevertheless, quality control is still very important in the domain of MEG. Also to make sure that your data is valid and that you can run analysis on it, because it might happen that something like this happens. So for example, here you can see that something with this channel is clearly off. So there is like very high deflection, which is not usual. You can see the usual channel here. So in the domain of MEG, there could be several sources for artifacts. First of all, there could be environmental artifacts. So for example, the power line artifact. The power lines produce static magnetic fields at a frequency range of 50 or in the US 60 Hertz. Also, there might be biological artifacts like the heartbeat of the participant, which is measured in the MEG, or ocular movements also produce magnetic fields. Also, of course, sensors could be broken, or anything else could be wrong with the setup. So it could also be due to systemic malfunction or failure in setup that the data is corrupted. So what is MEG-QC now? MEG-QC is a tool which seeks to somehow standardize quality control workflows in the MEG domain. This is also because right now, to my knowledge, the MEG community is missing tools or standards with respect to quality control. Moreover, MEG-QC is designed to lower the entry bar to QC in the MEG domain for early career researchers, and also speed up data inspection or QC routines for more experienced researchers. It is easy to use and intuitive, and also provides exhaustive description of the data through interactive HTML reports and machine interoperable JSON files. It interfaces with the BITS standard, also writes these reports back into the derivatives folder of a BITS dataset, and is mainly based on MNE and Plotly. If bits doesn't mean anything to you yet, don't worry about it, because you will be provided with more infos on bits in a later session. But let us now have a look at how researchers can visualize their MEG data using MEG-QC. Okay, so here you can see a report which is produced by MEG-QC. On the left side, there is a table of contents that comprises all the information which you can find in these reports and all the metrics which are computed on the data. Due to time limitations, I will not go through the whole report today, but focus on the plot of the power spectral density, since for electrophysiological data, it is very important to visualize the data in the frequency domain to detect artifacts. So we can just now click on frequency spectrum here to get to the PSD plot. So what you can see here is the power spectral density for all of the 306 channels. This on the left side here, you can see a list of all of the channels. You can now play around with these plots. For example, you could, if you want to zoom in, because clearly here there is a peak at 11.5 hertz. So you could basically just zoom into this to take a closer look. I will reset it now. You can also basically just hover over any data point, and it will give you the exact values plus the channel name. Also, if you don't want to look at all of the channels, you can single out channels by double-clicking in this legend here. They are now organized by lobes, which are defined in a paper by you and colleagues. But you can, like this, you can single out all channels of a lobe. And if you want to look at a single channel, you basically just click once on all of the other channels, and you will basically just be left with whatever channel you want to look at. So this would be a single channel now. If some researchers prefer to look at their data on a different scale, so you could also, for example, change the scaling here. So you could look at it, the y-axis on log scale, in a log scale, or you could look at your data in a log-log scale, so x-axis as well as the y-axis in log scale. There is also, you can also, if you, for example, have zoomed in, you can also use this pen to basically inspect the data outside your zoom range, basically. Yeah, and that's about it for my short introduction to the interactive features of the MEG-QC reports. Thanks for listening.